So let me go back to the basics in some sense. So Bayes' theorem, which is outlined there in equation 1, gives me a way of computing the probability of observing event A, given that I observed already event B. This relationship, equation 1, is going to be present throughout all the exercises and all the points we covered today. Although not necessarily in that way, but applying this theorem to random variables rather than to events, because as you know, and as Andre mentioned in previous video, Bayesians treat parameters, regression coefficients, and missing data, for instance, as random variables that have a certain distribution. So in the context of Bayesian statistical inference, we're going to start from a parameter like theta, from which we want to draw inferences. This parameter is a random variable and thus has a certain distribution, which is denoted by f theta. And in addition to that parameter and its distribution, we're going to have data, and we're going to denote by f data given theta, the sampling distribution, or roughly the likelihood of the data, right? And in the context of Bayesian statistical inference, we're going to work with equation 2, which is Bayes' theorem applied to random variables, and in particular applied to a parameter of interest theta. So in equation 2, in the numerator we have f theta, which is what Bayesians call the prior distribution of the parameter, which in some sense this can be understood as the probability distribution of the parameter before we observe any data. This is obviously a simplification, but suppose we start with some prior beliefs about how the parameter behaves, summarized in the probability distribution f of theta. We then have f of data given data, which, as I said, is the probability distribution of the data, which is something you work with and you are familiar if you have worked with maximum likelihood estimation, for instance. And what we want to compute is what we denote as the posterior distribution of theta, the posterior distribution of the parameter, f of theta given the data. So this is the version of the Bayes theorem that we are going to work with when we do Bayesian inference. And from equation 2, and given that f of theta, as it's stated there, is independent of my random variable, which is my parameter, we can simplify this and work with equation 3, which essentially is what I would call, or I call in the slides, the Bayesian mantra, which is the posterior distribution of the parameters of interest is proportional to the likelihood of the data times the prior distribution. And we're going to use this relationship throughout the slides, throughout the exercises included in this with the slides, and throughout your Bayesian life, right? The posterior distribution of a parameter is proportional to the likelihood and the prior. Okay? So in some sense, and very informally, when we do Bayesian analysis, we start from a prior distribution, what we believe about the behavior of a parameter before observing the data. We then observe the data, and we update our prior beliefs about that parameter once we see the data, and arrive at the posterior distribution of the parameter. Okay? And the whole purpose of Bayesian inference is exactly deriving the posterior distribution of theta, starting from the prior distribution and again, very informally, my beliefs about the parameter, for instance, and the likelihood or the distribution of the data, right? So essentially, I would say that Bayesian inference, the whole big world of Bayesian inference, can be summarized as a process that consists of 4 steps. First, we start from a likelihood, the distribution of the data, the x's and y's, the dependent and independent variables in our models. We then need to specify a prior distribution for the parameters of that model I'm examining, which in this case I'm summarizing all these parameters as, or denoting all these parameters as theta. Once I have the data and I have the prior, and step 3 is perhaps the key step, which is deriving the posterior distribution, which is in some sense the most difficult step. And finally, once I have derived the posterior distribution, I can summarize it, computing posterior mean variances, reaching posterior, what we know as posterior summaries. So let me walk you through a simple example of how these 4 steps are applied in practice. Suppose I have 2 candidates, A and B, competing in an election. And you're going to have to excuse me for using a political science example, but I am a political scientist. So we have A and B, 2 candidates running for office. And suppose we have an opinion poll based on a representative sample conducted before the election, a poll with 1,067 potential voters, 556 of which stated they would vote for A, 511 declaring they would vote for B. So based on this data, candidate A hires a Bayesian researcher so that this researcher estimates the probability that A wins. Okay, so let's go over the 4 steps of Bayesian analysis in this instance. Step 1, as I mentioned, is specifying a model for the data. In this case, and suppose I am ignoring the possibility of abstentions, I have 2 possible responses for each individual who participated in this opinion poll. We have 2 potential answers to the question, who would you vote for? Vote for A or vote for B? So we can think of this. Remember, we have an opinion poll with 1,067 respondents. We can think of this as 1,067 independent Bernoulli trials, where the success is voting for A, voting for candidate A. So we're going to denote by P the probability of success, and by Y sub B the choice that individual I makes, and I can take 2 values. 1 if I would vote for A, or 0 if I would vote for B. So we can think of the sampling distribution of the data as what we observe in equation 4. Right? So for each individual in the sample, yes, a probability P of success and a probability 1 minus P of failure, or again, success being voting for A and failure being voting for B, especially because the Bayesian was hired by A. So based on the responses to the public opinion poll, we arrive at this distribution of the data, which we see in equation 5. Now, as I said, again, going back to the Bayesian mantra, the posterior distribution of the parameters, in this case, the parameter is going to be P, the probability of success. This is a simple example with some Bernoulli example. So the parameter of a Bernoulli distribution is P, the probability of success. So going back to the Bayesian mantra, which is posterior is proportional to the likelihood times the prior, what we have is that the posterior distribution of P, given the data, is going to be proportional to the sampling distribution times the prior, which I will denote by f of P. And this takes us to the second step of the Bayesian analysis. Remember, I said any Bayesian analysis has 4 steps. Step 1, specifying the distribution of the data. Step 2, choosing the prior distribution for P. So we need to choose a prior for P, and it turns out that a typical prior distribution for parameters that represent proportions or rates is the beta distribution. Right? Specifically, the beta is what we know as a conjugate prior distribution. A conjugate prior is a prior such that the posterior follows the same distribution of the prior, which is, as we will see in several examples, is very convenient. So what I'm saying here is that if I assume that the P has a beta prior, the posterior, which I still don't know how it looks like, but I know it will be beta. Just a side note, why beta? Well, because beta, as I said, is used as a prior for proportions of rates because it has a very nice property of essentially bounding the parameter between 0 and 1, which is what I want from beta. And you can play with a code there, which I include with these materials, called beta distribution R, which allows you to compute different values or obtain different beta distributions depending on what I will call here the hyperparameters of the distribution. Right? So alpha and beta are essentially control how or the shape of the prior distribution. Okay, so here we have a graph of betas with different combinations of parameters, and alpha and beta, which control the form of the prior, are known as hyperparameters. And these hyperparameters will influence how much weight the prior distribution has in the posterior distribution. Essentially, it's hyperparameters, and this applies to the beta distribution, but to any distribution in general. The hyperparameters of a prior distribution, in some sense, control how much influence the prior distribution is going to have relative to the data in the determination of the posterior distribution. Let me give you an example. Suppose I have no prior information at all about alpha and beta, or about the parameter P. The parameter P being the probability of voting for A. Suppose I have no idea, I have no information at all. Well, one way of incorporating this lack of information into the beta distribution is choosing alpha and beta equal to 1. Why? Because as you can see here, when I choose alpha and beta equal to 1, I end up with a beta distribution that's degenerate at 1. Or another way of putting this is that when I combine my data, the likelihood for the data, with a beta prior with parameters 1 and 1, it turns out that the prior essentially incorporates no information at all. Or another way of saying is that the posterior is going to be completely determined by the data, right? This type of, or mainly determined by the data. So this type of prior distributions that incorporate very little information to the data, essentially this type of priors in which the posterior form of the posterior is essentially determined by the data and not the prior, are called vague or weakly informative prior. Okay? You can see here the posterior distribution for P is essentially proportional to the likelihood of the data, and the prior, in some sense, vanished. Now, let's go to the opposite extreme. Suppose that in addition to the poll I am currently analyzing, there are several other polls that were conducted last month, 2 months ago, 3 months ago, and supposed to make things very simple, that I want to incorporate all that information. Right? I want to use the results from previous polls and incorporate them in the prior, and use that to inform my inferences and essentially in the derivation in the posterior distribution of the parameter. Well, one way of doing that is using the same beta distribution, which I said is a conjugate prior. So having a beta prior leads to a beta posterior, which is nice in the sense that I know the form of the beta distribution. But now, instead of having parameters alpha and beta equal to 1, I'm specifying the alphas and betas based on or incorporating all the information from the previous polls we conducted before dealing with the polling question. So I use those priors, and the posterior now is going to be quite different. The posterior, turns out, is going to be heavily influenced by the prior information. Right? So, and we are already in step 3 of Bayesian inferential procedure. What we have is that starting from a likelihood for the data and having chosen the prior distribution for the parameters, in this case P, we arrive at the posterior distribution for the parameter. And this posterior distribution is going to be, the form of the posterior is going to depend on the data, but also on the priors, specifically in this particular example, on whether I use vague priors, which added very little information to the beta parameter, or I use more informative priors, for instance, incorporating information from previous polls. Finally, I said the last step of any Bayesian analysis, step 1, defining the likelihood, step 2, defining the priors of the parameters, step 3, deriving the posterior, and finally, summarizing the posterior distribution, because, and this is again a key difference between Bayesian inferences and classical inferences in statistics. I don't get an estimate for P. I don't get a point estimate as one would typically expect in Bayesian setting. What I get, the result of my Bayesian analysis is this: a posterior distribution, which is great, but the client who hired the Bayesian statistician doesn't really understand what it means to have posterior distribution. What the client wants to know is, well, what's the probability that I will win the election? So I need to summarize this posterior distribution in some way. I can compute then the posterior mean. I can compute the posterior variance. I can compute credible intervals, right? So for instance, the posterior mean, because I know that the posterior distribution is beta, because the prior was beta, and beta is a conjugate prior, meaning the posterior is going to have the same beta distribution, also a beta distribution with different parameters, but a beta distribution. I can apply the formula for the expected value of a beta distribution to compute the expected value of P. I can compute also credibility intervals for P. I can compute things like, well, what's the probability that my client A wins? Well, that's a probability that P exceeds 0.5. What's the probability that my client A loses? Well, that's the probability that P, the probability of success, is less or equal than 0.5. So I can, from the posterior distribution, I can compute all those quantities. Okay? And essentially, that's a first exercise in Bayesian computation. I just want to show you that, obviously, how close the posterior is to the prior, or another way of saying it, how much importance the prior vis-a-vis the data has on the posterior depends on my choice of priors. So remember that in one case, I use informative priors, meaning I incorporated the information from several previous polls into the analysis. In this case, turns out that the posterior is very close to the prior. However, when I use vague or weakly informative priors, alpha and beta equal to 1, my example, turns out that the posterior is closer to the data. Another way to say this is if you use vague priors or weakly informative priors, the form of the posterior is going to be primarily influenced by the data.